The first thing on here is just kind of a review. We are talking about the population proportion. That's our p hat, which we have looked at several times already. So just a refresher, p hat, remember, is x over n. That's on our formula sheet. For it to be normal, we have to check that n times p times 1 minus p is greater than 10, and the sample has to be less than 5% of the total population. So we'll be making sure when we do these problems, we'll have to verify our criteria still. Mean, we know from before, is just your p, and our standard deviation is p times 1 minus p over n. So all of that is old stuff that we were using on the last test. When I talk about something being statistically significant, that means that the result that we get would be unlikely if the null hypothesis is true. So remember yesterday we said we will assume the null hypothesis until proven otherwise. So if I'm assuming the null hypothesis is true, and I get that there is a 1% chance of something happening, would that be statistically significant? Yeah, 1% would be very, very rare. So that would lead us to believe that maybe the null hypothesis was not true, in which case we would look at the alternative hypothesis. So what we're going to be testing is we're trying to find out if things are significant enough to allow us to decide if we should reject or fail to reject the null hypothesis. Remember, yesterday we talked about writing a null and an alternative hypothesis, so let's do that for this example. A researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving. So p hat is 534 over 1,000. We've done that before. Does this suggest that more than 50% of people favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is some proportion less than 0.5, and we just happen to survey a majority? Okay. In other words, what we're trying to decide, would it be unusual to obtain that sample proportion? And what would be convincing? So we'll be looking at problems like this. We'll have to start out with the null and alternative hypothesis. We are talking about p hat, and that is going to be the case for everything that we're doing today. We're going to be looking at our proportion. Typically in the null hypothesis, we're not going to put it as p hat. We're just going to put it as p. Here's why. We need, the null hypothesis is like what we are believing to begin with, and your p hat is what comes from the sample. So when we're looking at this, we're trying to decide if it's possible that more than 50% favor the policy. So my null is going to be that p is equal to 0.5, that the proportion is 0.5. We will always do p, the null hypothesis will always just be equal to. Okay, for our purposes, where we're starting with this, we have to just set up our null like that. Then my alternative is going to be what? We are trying to find if it's greater than. Another clue, your p hat, was that more or less than my 0.5? P hat was more, so I'm trying to figure out, does that mean that my real proportion should be more? Okay, so that's my null and my alternative. There are two ways that we can test this. The first one is what's called the classical approach. I will teach this to you. I think one homework question will ask you to use the classical approach, but I don't use this one as often. I think the second approach is going to be easier.
But we have to do one on the test.
On the test, I will not say that. I'll just ask you to test it. So whichever way you do it is fine. Okay, cool.
Yeah.
Do you have a headache?
A little bit.
Do you want me to turn off the light? Would that help?
If you turned off all of them.
I'll turn it off.
But wait.
Does that help?
That is amazing. Thank you.
You'd be looking like JoJo in bio.
No, I just closed them whenever I wasn't looking at anything.
So to test the classical approach, we will be just looking at how many standard deviations we are from the null hypothesis, and essentially if you're too many standard deviations away, we would say that we have to reject. Now, the question is, I say if it's too many standard deviations, I haven't really told you how many standard deviations that might be, because it varies slightly per problem. You know, if I'm just trying to figure out, what was this example we were using? The voters who were in favor of banning cell phone usage. Okay, that's something that, sure, I want an accurate answer, but it's not a life or death type situation. So if I'm not completely accurate, nobody's going to get hurt. But if I am testing a new COVID vaccine and I want to know if it's safe, would you want to leave a 10% chance that maybe it's not? No, sometimes we're going to have to be more accurate than others. So there's not just a guideline that 2 standard deviations, anything beyond that doesn't work. Because there are some scenarios where I need to be very, very accurate. So 2 standard deviations may not be enough. I might need to go out to 3 standard deviations or something like that. So in each problem, I will be kind of giving you a benchmark. You know, this is how accurate we have to be. So if we're going to do this, first thing we have to do is make sure it is normal. So we have to check our criteria. My sample has to be less than 5% of the population. What was my sample? 1,000. Is 1,000 less than 5% of all registered voters? Okay. And then my second thing, we need the n times p times 1 minus p to be greater than or equal to 10. So my n was 1,000. My p, that's the p that we're testing, so that's the 0.5. 1 minus 0.5. Should be 250, right? And that's greater than 10, so it checks. So what that means, I checked my criteria, it's normal. So then, just like any other problems involving p-hat, we are always trying to find probabilities, so we had to have the mean and standard deviation. We're still going to need that stuff. So the mean is just equal to p, which is 0.5. Standard deviation is square root of p times 1 minus p over n. You get 0.015811. All right. So all of this should seem familiar because this is how we started all of our problems on our test. You had to make sure it was normal. You had to find your mean and standard deviation. Okay, if we think about what that means. So our mean is 0.5. The standard deviation, to get these amounts, you'd have to do 0.5 plus your standard deviation and 0.5 minus your standard deviation. So this would be 0.51811. And this would be 0.484189. Do you guys see where I got those numbers? All right, so essentially that's within 1 standard deviation. If you wanted within 2 standard deviations, what would you do? Do it again. You could add or subtract it again. So we could set it up like that. We can also go back to talking about our z's. Now I have to tell you how many standard deviations I'm using here. So let's say I said I want to reject it if our proportion is more than 2 standard deviations from the mean. The reason a lot of times I will use 2 standard deviations, because if you're looking at your normal table, what is the probability that z is greater than 2? Let's look it up on our table.
0.1.
So if our z is 2.0, and you would have to do, for greater than, 1 minus. And so we get 0.0228. So there is only a 2.28% chance of being more than 2 standard deviations above that. So is that enough to be unusual? Yeah, anything less than 5% is unusual. So that's why 2 standard deviations is one that we'll commonly use if we were doing the classical approach, because that would give us unusual data. So if I want the z-score, just like on our test, it's your value. So my p-hat value was what?
0.53.
Yeah. Minus our mean, which was the original p of 0.5, divided by the standard deviation. And we get 2.15. So what this says is it is 2.15 standard deviations above the mean. Above because it's positive. So would I reject the null hypothesis in this case? Yeah, the classical approach said we would reject if it's more than 2 standard deviations. It's 2.15 standard deviations, so that would be enough to reject. So that's the classical approach. Essentially, you have to have some benchmark for how many standard deviations above the mean. You find your z, and if it's more than that, you reject. I prefer to use a second approach called the p-value approach because it aligns really, really well with everything we've been doing. So it's very similar, but instead of just looking at standard deviations, we'll just go ahead and find our probabilities and reject or fail to reject based off the probability itself. So essentially, I will give you an alpha level. So I'll say alpha equals 0.05. And so if your probability is less than that, you would reject. Okay, so you'll have some level given in the problem. You find your actual probability just like we did on the last test. And if it's more than that, you fail to reject. If it's less than that, then you can't reject. Our p-value, there's going to be a couple homework questions that ask you to interpret what your p-value means. So you might put a star on the slide. It will help you. What we're finding is the probability of this happening if the null hypothesis is true. So we are assuming the null is true. So if I get that there is a 15% chance of this happening if the null hypothesis is true, is that unusual? No, so that's not evidence to believe that my null is false. But if I got a 1% chance, that is convincing that something is not right and maybe my null hypothesis is not true. We will have to consider whether we have, yesterday we talked about left hand, right hand, and two-tailed, or left-tailed, right-tailed, and two-tailed. The one we were looking at, greater than, so is this which type of test is this? Right-tailed. That's a right-tailed test. The one that will possibly require a little more thought is the two-tailed test. Left and right are going to be pretty straightforward. So what we will do, we'll have our hypothesis. It'll be one of these 3 types, just like we talked about yesterday. In this section, we're always doing the population proportion, so P is always going to be our parameter. We'll have an alpha level, depending on the seriousness of it being wrong, seriousness of type 1 error. The classical approach is what we just got done doing, where we find our z and we compare it to a critical value, our standard deviations. And then we make our conclusion based off that, like we did on the last one. The p-value approach, it all starts out the same. You're still going to find your z. This is the formula given in the book, but it's easier if we just think about it the way we've been doing it. You know, this looks different, but my denominator here is just the standard deviation. So it's all of our regular z calculations. Then we'll get our probability, our p-value. And if the p-value is less than alpha, we reject. So this is the approach that I am going to use. All right. And then at the very end, we will usually write a sentence or something to clarify. At least we need to state if we reject or fail to reject. If it asks for more explanation, then we might have to elaborate a little bit. So let's look at a problem. We are actually going to do everything here. In 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 stated they did not trust the media. At the alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans who do not trust the media to report fully and accurately has increased since 1997? Your first step, you have to have your hypothesis. We're testing a hypothesis, so we have to know what my hypothesis is. Our null is always going to be p equals something, and that's like your baseline value. What is my p to start out with? 0.46. My alternative, I'm trying to test if it has increased. So my alternative is p is greater than 0.46. All right, so if you're looking at our steps, step 1 we said hypotheses. Step 2, we said you need your alpha. What's our alpha here? 0.05. You don't necessarily have to write that down, but I'm just trying to follow the steps that I gave you. Step 3, what do we have to do? Yeah, we need to get our z. Before we calculate a z, we should verify our criteria. My sample is 1,010, so is 1,010 less than 5% of the population? Yeah. My n, 1,010 times p, 0.46 times 1 minus p. Verify that that's greater than 10. And it is. So my criteria is good. We should check that because we are going to talk about today what to do if that criteria isn't met. So it's not just assumed that every single problem I give you will meet the criteria. You do need to make sure. Because this meets the criteria, that means it's normal, so that means we can find our z. If we're going to calculate a z, we need the mean and standard deviation. So the mean is just our p-value. Standard deviation for p hat is the square root of p times 1 minus p over n so we get a standard deviation of 0.015682. So the criteria, the mean and standard deviation, this is what we were doing on our last test. Finding our z value, that's like what we've done before. So if we find that, we take our value. Well, my value is my p hat, isn't it? Have I stated, did I state in the problem what p hat was? Can we find it? Yeah, p hat is x over n. Try not to round this a ton. It can cause some problems if you have a lot of rounding error. So I'll just keep a few decimal places there. You don't have to be crazy with it, you know, I don't need 10 decimal places, but try to round it to more than just 1 or 2. So we get 0.5198 minus my mean, which was 0.46, divided by the standard deviation, which was 0.015682. So I get a z value of 3.81. Again, depending on how you rounded things, it is possible that your z may not match mine exactly. That's why it is so important for you to write down the numbers that you are using in your problem. All right. So then let's talk about the 2 different approaches so you guys can kind of pick. The classical is what we just talked about. Because this one is an alpha of 0.05, you have to think about the z alpha like we had in our last test. So if the area to the right is 0.05, what's the area to the left? 0.95. So to find your z, you have to go to the table. You're looking inside the table to find 0.95, or as close as we can get, and then the z that matches that. So 0.95 would be 1. It's right in between 1.64 and 1.65, so 1.645. And then you just compare these z values. Sometimes if you're looking, we might call this z sub 0, just meaning the z for the null hypothesis. That way, if you have multiple z's in your problem, it's less confusing to you. Essentially, what we see is since my z of the null is bigger than my z alpha, so that means my z is further above this. Would that tell me to reject or fail to reject? Basically, at 1.645, anything beyond that we would reject because it's outside of that window. So 1.645 is my threshold. 3.81 is higher than that, so it's further away from the mean, so we would reject. The p-value approach. This is the one I prefer. We have a z value. We know from our last test how to find probabilities for this, right? If you're looking at your normal table, what do you notice about a z of 3.81? It's not on here. The closest we can get from our table is 3.49, so we'll just use that probability. That's as close as we can get with our table. We know that this would be even smaller. So the closest we can guess for finding the probability that our z is bigger than 3.81, you would have to do greater than is 1 minus the probability from the table. And again, this isn't perfect because our table doesn't go that high. But what we found is there is a 0.02% chance of this happening if the null hypothesis is true. So how does that make you feel about the null hypothesis? Probably not true. My alpha level was 0.05. That tells me anything smaller than 0.05 makes us reject. So that probability is less than alpha, so we reject. So I like the p-value. I think it's less confusing. You're not looking up a z, you're just reading probabilities like normal. There'll be an alpha given in the table, so if your probability is smaller than alpha, you reject. I think it's a little more straightforward. I would also like to talk about how to do this on the calculator, if we could. so everybody would grab their calculator. So we are going to go into our stat tests like we were doing in the last chapter. And this time we are actually testing. Now when we're talking about P's, remember when we did like confidence interval, we were doing a 1 proportion Z interval because when you had P as your parameter, it was always the Z interval. We actually want to go to number 5 here. We're going to do a 1 proportion Z test. Okay, then it's going to ask us some questions. Our P sub 0, that is the P in our null hypothesis, which was 0.46. Our X was what? Our N. Okay, then you have to pick what are you testing. Are you doing not equal, less than, or greater than? This one, our alternative hypothesis was greater than. We're going to go to calculate. Draw it shows you a picture of the normal curve and what you would expect. We just want the actual numbers associated with it, so we'll go to calculate. So this gives us Z equals 3.81, which is what we had. And then our P. This is not the same P we got by hand. Why? Yeah, did our table even go up that high? We just kind of estimated. This tells us that E negative 5, it's 0.40685, so it's even smaller than what we estimated. As in a normal problem, these things would be closer to one another. They are probably not going to be exact very often because we are rounding all of our Z's to 2 decimal places so we can look them up in a table. Your calculator is more precise. It doesn't have to just use numbers from the table. So its probabilities are always going to be slightly different than yours. They will be close, but they are going to be more accurate than what we are able to do with our table alone. Questions? Okay. Let's try another one. So I'm going to kind of abandon this classical approach now, and I'm just going to do the rest of them with p-value approach. So when asked, is it more important to protect the rights of Americans to own guns or to control gun ownership? 46% of all Americans said protecting the right to own guns is more important. A research center surveyed 1,267 randomly selected Americans with at least a bachelor's degree and found that 559 believe protecting the right to own guns is more important. Does this result suggest the proportion of Americans with at least a bachelor's degree feel differently than the general population? Use alpha equals 0.1. All right, so step 1, we always need our hypotheses. The null would be what?
Equal to 0.46.
Mm-hmm. Okay, the alternative would be what? I want to know if they feel differently.
Equal to?
Not equal to. So it could be that they are more likely, could be that they are less likely. I just want to know if it was different. All right, what is our alpha level? Okay. So that's a pretty generous alpha, 10%. We should check our criteria. 1,267 is less than 5% of all Americans, so that's good. N times P times 1 minus P. So is that bigger than 10? Okay, so that one's good. So that means we can go on assuming it's normal. So step 3, we have to get our Z. So to do that, we need a few things. We need our mean. We need our standard deviation. Our mean is just your p's, so 0.46. Standard deviation is the square root of 0.46 times 1 minus 0.46 over n 1,267. And I get a standard deviation of 0.014002. We are also going to need our p hat in this problem. P hat is x over n. What was my x? And my n? So my p hat is 0.4412. So now let's find the z. You can call it z sub 0 for the z of the null if that helps you just kind of organize your stuff. So we do our value, which is the p hat, minus the mean, divided by the standard deviation. So I get a z of negative 1.34. Okay. Remember at the beginning I said two-tailed test is kind of different? Let's find the probability of this, because we're just going to do classical approach. Or sorry, not classical, p-value approach. So less than negative 1.34 would be 0.0901. But since we're doing two-tailed, okay, here's the center. We're just trying to find not equal to. Okay, we just found the probability of this tail, but it's two-tailed, so it could also be over here, right? These two probabilities are equal. So what should I do with this number?
Make it negative.
Well, the z would switch, but if I just want the probability itself, those would both be the same, wouldn't they? So if I want the probability of being in either one of those tails, you just have to multiply it by 2. That is always the case for the two-tailed. You have to take your probability times 2 because it could be in either one of those tails. So if I do that, we get a final probability of 0.1802. So the probability of this happening, if my null hypothesis is true, is 0.1802, 18%. So do I fail to reject or do I reject?
Yeah.
Right. You reject if your probability is smaller than alpha. Since this is greater than my alpha, which was 0.1, we fail to reject. Does that mean the null hypothesis is true?
No.
No, it just means I haven't proven it's false. For practice, let's try this one in the calculator too, make sure we know. Just like most of the things that we've done, I'll ask you to do one by hand, and then, if you can do it by hand, you can do the calculator.
I just did that one on the calculator and it gave me 0.1794.
Because remember I told you that your calculator is more exact, so it's
Okay.
not going to give you the exact same answer. So we go to stat, tests, we want number 5, the one proportion z-test. So our p hat was, or our p of the null was 0.46. Our x was 559. My n, 1,267. And we were testing not equal. Then when we calculate, so this gives me a probability of 0.17937, which is not the same as we got, but here's why. We rounded our z to 2 decimal places. They used the exact z and found the exact probability. So if you're doing this on the calculator, it will be slightly different, but they're still really close. Okay, they're not going to be very far off. Is that one okay? Another method of testing it, you can use the confidence interval that we've done. We've built confidence intervals before. So you could do the confidence interval like we were doing on our last test. And then if your null hypothesis is in that confidence interval, then we fail to reject. And if your null hypothesis is not, then we could reject. So let's try one using the confidence interval approach. So a 2009 study found that 34% of teenagers text while driving. A more recent survey found that 353 of 1,200 randomly selected teens had texted while driving. Does this suggest the number has changed? Use a 95% confidence interval to answer the question. So we still need our hypothesis. The null hypothesis is that the proportion is equal to what? 0.34. What is my alternative? I just asked if it has changed.
So not equal to.
So not equal to, yeah. The P is smaller, so I might have asked, has it decreased since then? You just have to watch the wording of the question, which way they want us to find it. So if we were going to build a confidence interval for P hat, look at your formula sheet. So remember we did these confidence intervals in chapter 9. So we had P hat plus or minus the alpha over 2 times the square root of our P hat 1 minus P hat over n. So if I want to do that, we're going to need our z value, which we can get from the table. Since I said a 95% confidence interval, then my z would be, if you look down at the bottom, 1.96. Before we assume it's normal, let's check. Is 1,200 less than 5% of the whole population? Yeah. My n, 1,200, times my p, 0.34, times 1 minus p. That's bigger than 10, so we can assume it's normal. So I didn't write it down, but I did check my criteria. All right. We need our p hat in this formula as well. So p hat is x over n. So that is 0.2942. We know we can do confidence intervals by hand or on the calculator. I don't care if you do it by hand. Your p hat is 0.2942. You'll have to do a plus and a minus for your upper and lower. Your z is 1.96. Square root of 0.2942. 1 minus 0.2942 over my n, which was 1,200. So if I plug that in for the minus, I get 0.2684. The plus, I get 0.31998, so that's 0.320. Do you guys remember how to do confidence intervals on the calculator if you wanted to? Since we're talking about your stat test, when we're talking about the p's, we're doing the z interval. So that was, my calculator froze. A that you would go to there if you want to do it on your calculator, and you could do either. So then what we look at is, does this interval contain my null hypothesis? No. So the interval doesn't contain my proportion of 0.34. So we know with our p hat, 95% of them should fall within here. So if my null hypothesis is not in there, what would that tell me? Reject or fail to reject? It's not in your confidence interval, you can reject. Okay. I have one example left, what to do when this does not meet the criteria, so that's the only thing I haven't gotten to. I will do that right at the beginning of class tomorrow. It'll just take me a few minutes. And then the rest of class will be